Look up. Right now, wherever you are, look up at the sky. It seems empty, quiet, blue. But it is a lie. A beautiful, fragile lie. Up there, hidden in the glare of the sun and the blackness of deep space, there is a ticking clock. We call them near-Earth objects. You call them asteroids. There are millions of them. Chunks of rock and iron left over from the birth of our solar system, flying at speeds 10 times faster than a rifle bullet. We have all seen the movies. We have watched Bruce Willis save the planet, or we have seen the horror of Don't Look Up. We think of an asteroid strike as a single event. One big rock, one big boom, the end. But that is not the true story. Today, we are going to ask a question that keeps planetary scientists awake at night. Not a hypothetical fantasy, but a statistical certainty if you stretch the timeline far enough. What if every asteroid hit Earth at once? Not just the big one, not just the dinosaur killer. Every.
To understand the end, we first have to understand the scale of the threat. Right now, as you breathe, there are roughly 1,000 known asteroids larger than 1 kilometer in diameter, buzzing around our neighborhood. These are the planet shakers. If one of those hits us, humanity doesn't go extinct instantly, but civilization ends. We go back to the Stone Age. But that's just the big ones. If we look at the smaller rocks, the ones the size of a house or a football field, the numbers explode into the millions. In the main asteroid belt between Mars and Jupiter, scientists estimate there are over 750,000 asteroids larger than a kilometer, and billions of smaller fragments. But here is the terrifying part. They aren't all staying in the belt. Jupiter's gravity acts like a giant slingshot, hurling these rocks toward the inner solar system, toward us. Now, I want you to imagine taking a map of the world. I want you to imagine taking every nuclear weapon ever created, every warhead the US, Russia, China, and the rest have ever built, and stacking them together. The resulting explosion would be terrifying. It would be nothing compared to this. If you took the asteroid that killed the dinosaurs, a rock about 10 kilometers wide, roughly the size of Mount Everest, and dropped it on New York, the energy released would be equivalent to 50 million.
Now, take that energy, multiply it by 1,000 for the kilometer-wide rocks, multiply it by 1,000,000 for the city killers, and then add the billions of tiny impacts that happen every single day. We aren't talking about an impact. We are talking about a collision. A moment in time where the Earth stops being a planet and becomes a target. Let's press play on the apocalypse. Let's say, for the sake of this true story, that the gravitational chaos of the solar system suddenly syncs up. Every rogue rock, every dormant comet, every piece of debris decides that today is the day. It is 12 p.m. Greenwich Mean Time. The first thing you notice is the light. Before you hear the sound, before you feel the shake, you see the sky turn white. According to impact simulations like the Asteroid Launcher program, the largest asteroids, the 100-kilometer-wide planet killers that scientists estimate would be required to truly sterilize Earth, hit first. They are moving at 20 kilometers per second. As the first of these monsters touches the atmosphere, it doesn't act like a rock. It acts like a piston. It compresses the air in front of it so violently that the atmosphere turns into plasma. The temperature instantly reaches several million degrees. For a millisecond, the impact site becomes a second sun. The ocean boils. The rock turns to gas. But there is no time to process this, because the other million rocks are arriving simultaneously. Pop culture tells you that you would be vaporized by the blast. That's true, but the true story is much more horrifying. Within the first second of the all-at-once impact event, the crust of the Earth ceases to exist as a solid surface. Think of the Earth as a glass marble. Now, imagine throwing it into a furnace and hitting it with a sledgehammer at the same time. The initial impacts, specifically the dozen or so 50-kilometer-wide asteroids, punch straight through the crust. The crust is only about 30 kilometers thick under the continents. These rocks punch through it like bullets through tissue paper, exposing the mantle, the liquid magma core of the Earth, to the vacuum of space. The pressure is released. The result is the largest volcanic event in the history of the solar system. Supervolcanoes don't just erupt, the entire planet cracks open like an egg. But we aren't dead yet. Well, technically we are, but let's look at the physics. For those of us not standing directly at ground zero, say you were in a deep bunker in Kansas, you would have about 0.3 seconds to live. The fireball.
Asteroid impacts don't just make craters. They create expanding spheres of superheated gas. A 1.5-kilometer comet creates a fireball that kills for hundreds of miles. Now, imagine thousands of those fireballs merging. The heat radiating from the sky would be absolute. It wouldn't just set forests on fire. It would melt the surface of the soil into glass. It would vaporize the oceans down to the seabed. As one physicist put it, the energy released in that first second is roughly equivalent to the total energy output of the sun's core, but concentrated entirely onto the surface of the Earth. In space, no one can hear you scream. But on Earth, sound is a weapon. The Chelyabinsk meteor that hit Russia in 2013 was only 20 meters wide. It never touched the ground. Yet, the shockwave it generated when it exploded in the air circled the globe twice. It shattered windows and collapsed roofs for hundreds of miles. Now, scale that up.
As the all-at-once event unfolds, the atmosphere is no longer air. It is a wall of compressed fury. The shockwave from the dinosaur-killing asteroid carried enough energy to trigger earthquakes of magnitude 10 plus on the other side of the planet. In our scenario, the shockwaves don't travel. There is nowhere for them to go. The overlapping pressure waves from millions of strikes converge. The air pressure spikes instantly to that of the deep ocean floor. Your lungs would collapse before your brain could register the pain. But the sound isn't the killer. The sound is the courier. It is carrying the debris. We have survived the first minute. How? Well, if you were in a submarine, deep in the ocean, or in a bunker on the highest mountain peak, the initial heat and shockwave might pass over you. But now, the true story begins. The story of the impact winter. 66 million years ago, the single Chicxulub asteroid kicked up enough dust to block out the sun for years. It killed the dinosaurs not by the impact, but by starvation. The plants died, then the herbivores, then the predators. That was one rock. In our scenario, the amount of dust, soot, and sulfur injected into the stratosphere is almost infinite. Recent supercomputer simulations by scientists, published in journals like Science Advances and Physics World, show that even a medium-sized asteroid, just 500 meters wide, like the feared Bennu, would inject 400 million tons of dust into the sky. The result? A global temperature drop of 4 degrees Celsius. A nuclear winter effect that would last for years. Now, multiply that by a factor of 1,000,000.
The sky turns black. Not dark gray,
Not storm cloud black. Absolute zero. Infrared heat from the sun is cut off by 99.9%. Within 1 week, the global temperature drops to minus 20 degrees Celsius at the equator. Within 1 month, the atmosphere starts to snow frozen carbon dioxide. The oceans, which we thought might be a refuge, freeze solid from the top down. Without the sun, photosynthesis stops completely. The simulation models for a single large impact show that global net primary productivity, the growth of plants, drops by 36%. That is just from dust. But in our all-at-once scenario, we aren't just dealing with dust. We are dealing with the fire.
There is a silent killer in this story. It's not the rock. It's not the cold. It's the chemistry. Asteroids are made of different materials. Some are iron, some are stone, some are carbonaceous chondrites, full of organic and deadly compounds. When these rocks vaporize, they release their chemistry into the atmosphere. Specifically, they release massive amounts of nitric oxide and sulfur. Here is the science. The heat of the impacts causes the nitrogen and oxygen in our air to bond. This creates acid rain so potent that it would be like dropping battery acid onto the planet.
But worse than that, these gases destroy the ozone layer. The ozone layer is our sunscreen. It blocks ultraviolet B radiation. With the ozone layer gone and the dust blocking the sun, you have a paradox. The surface is freezing and dark, but if you step outside, the residual UV radiation leaking through the broken atmosphere would give you a fatal sunburn in seconds. If any microbe survived in the deep ocean, it would be safe. But any complex life, anything that relies on DNA, would be fried by radiation the moment the clouds parted. Let's talk about the ground beneath our feet, or what's left of it.
The Richter scale is logarithmic. A magnitude 8 earthquake is 10 times worse than a magnitude 7. The impact of a large asteroid is measured on a different scale entirely. When the all-at-once event happens, the Earth rings like a bell. Seismologists call this free oscillation. Usually, a large earthquake makes the planet ring for days. In this case, the cumulative impacts deliver enough kinetic energy to alter the Earth's rotation. Remember the physics: mass times velocity squared. When billions of tons of mass hit the Earth at a 45-degree angle, they push. The day shortens. The impact forces act as a brake, slowing the spin slightly. The day becomes 30 seconds longer. But the shift is the real killer. The angular momentum changes. The crust slides over the mantle. The continents rip apart, not by plate tectonics over millions of years, but by sheer mechanical force in a few hours. The Rocky Mountains and the Himalayas, which took eons to form, would be flattened or turned inside out by the seismic waves converging on the opposite side of the planet. We have forgotten about the water. 70% of the Earth is ocean, and a surprising number of asteroids in our thought experiment are hitting the water. The Chicxulub crater is underwater, partially, in the Gulf of Mexico. The impact created a tsunami that was 1,500 feet high. It swept across the entire planet. Now, imagine not one, but 10,000 ocean impacts. The water doesn't just wave, it displaces. For the first hour, the oceans are blasted into steam at the impact sites. For the next 6 hours, the empty space where the water used to be is filled by the ocean rushing back in, only to be met by the next wave of debris falling from the sky. By the time the dust settles, if it ever does,
the geography of the ocean floor has been rewritten. Deep-sea trenches become mountains. The water, now a slurry of vaporized rock, glass, and dead organic matter, becomes a thick, acidic soup. Life in the ocean, the plankton, the algae, the basis of the food chain, dies in the dark. The hydrothermal vent communities, which scientists recently speculated might survive an impact, might actually thrive briefly due to the heat. But even they rely on chemicals dissolved in the water. When the ocean turns to acid, they follow.
Is it possible to survive this? In the movies, the hero hides in a refrigerator or a bunker. Let's be brutally honest about the true story. If you are a tardigrade, a microscopic water bear, you're fine. These creatures can survive the vacuum of space, radiation, and extreme heat. They will inherit the Earth. If you are a human, you have a problem. Even if you build a bunker 5 miles deep, the surface above you is gone. The oxygen you breathe is produced by trees and plankton. Both are gone. Simulations of nuclear winter scenarios, which are essentially the same as an asteroid winter, estimate that even a regional nuclear war would kill 1 to 3 billion people from starvation. A full-scale global winter would kill virtually all complex life. In the all-at-once scenario, the air itself becomes toxic. The impacts generate cyanide gas from the burning of carbon-rich rock. You might survive the impact. You might survive the fire. You might survive the first year in a sealed bunker with stored food.
But you cannot survive the silence. When you finally open the door, there is no sky. There is no ground. There is only a glassy, smooth plain of vitrified rock stretching to the horizon, under a black sky lit only by the occasional flash of lightning caused by the static electricity of the dust clouds. You are alone. You are the last human. You have about 3 minutes before the toxic air kills you. Let's fast forward. 1 million years later. The dust has settled. The clouds have parted. A visitor from another star system arrives. They look down at Earth. They see a planet that is smooth. The craters, thousands of them, have been erased by the global volcanic activity. The crust is new. They drill into the rock. They find the KPG boundary, the line that used to mark the death of the dinosaurs. But above it, they find another layer. A chaotic layer of iridium, a metal common in asteroids, glass spherules, and shocked quartz. This layer is thick. It is global. They look for fossils. They find nothing.
No bones, no shells, no sign that a technological civilization ever existed. The heat of the all-at-once event was so intense that it didn't just kill life, it cremated the fossil record. Limestone recrystallized, granite melted. All evidence of humanity, the cities, the plastic, the nuclear waste, is vaporized or crushed into metamorphic schist. The only trace of us is a thin layer of unnatural carbon isotopes in the rock.